our team is going to bring you MilleMisceo, a product which will revolutionize the paint industry. Our team of engineers has been working on investigating a particular nanomaterial for its ability to enhance paint additives. But first, let me ask you, what's the most common coating that you encounter in your day-to-day life? Well, I mean, just look around you. It's paint. However, paint merely serves an aesthetic purpose in our lives right now. What if it could do more? What if we could insert an insecticide into our paints in order to kill off mosquitoes and spiders before they become a pest? What if we could introduce fragrances into our paints in order to make our rooms smell as good as they look? Currently on the market, there exist products that do this. However, they all fall prey to one phenomenon known as paint leaching. As your paint is subjected to heavy rain, to sunlight and high humidity, the additives that you add onto your paint can leach out. One, that makes it less effective, as your fragrances which you paint this month might not be so effective in a month or two from now. And the insecticides which you have applied to an external surface might leach out into the water table, causing massive ecological damage as they are incredibly toxic to fish. And this problem is endemic to the entire industry. Currently, all of these companies only focus on short-term effectiveness, selling you the properties of their product at the peak of its effectiveness. None of these products that we've looked at long-term integration. And this is a huge problem for a burgeoning market. According to a market analysis done in 2010, the paint additive market is expected to increase by 30% in the next 4 years. We at MilleMisceo believe that the leader, the one that comes out on top, will be the companies that focus on long-term integration of their additives into the paint, rather than a simple short-term effectiveness. And that is the MilleMisceo advantage. MilleMisceo provides this control. Simply by adding your additive into MilleMisceo and mixing that substance before introducing it into your paint, you can increase the lifetime of your additive in addition to preventing it from leaking out. Our job at MilleMisceo was to look at three things. One, to ensure that your additive could be loaded onto and released from the molecule. Two, we had to ensure that MilleMisceo didn't adversely affect the color or the gloss of the material that you had chosen. And third, we had to ensure that the product was actually market viable, that it was cheap enough for consumers to use.
So all of these are achievable. And we wanted to focus on the design of a product that we could use nanomaterials in order to achieve all of these design goals. So if you think about a conventional paint film, the typical mechanism by which all of these additives leach out is through simple diffusion. They're present in the paint matrix, and even if there's other materials mixed in with it, they tend to gravitate towards low concentration, which would be that paint and air interface. By introducing a nanomaterial into the paint, we can have a series of desorption and adsorption steps that slow down this diffusion process and give us control over the release of the additive. By extending its lifetime, we can also extend the efficiency and the effectivity of higher concentrations in the paint film. So, we have a concept, but how do we move forward without spending a lot of money on evaluating nanomaterials? We decided to do simulation testing. So, this is fixed second law of diffusion. It shows, it uses a diffusivity coefficient in order to simulate how quickly a concentration will evaporate, or sorry, not evaporate, but will leak out of a polymer film. So we started with a diffusivity value. This was industry research done by a company called Aptifer, and this is the diffusivity of an insecticide in a paint film called Permethrin. It's a neurotoxin, and we are actually later on purchased and tested this in experimental. When we included the energetic barrier that would be due to a nanomaterial interacting with this additive, which is permethrin, we found that a 4 order of magnitude smaller diffusivity coefficient would result. This effectively changed the amount of effective This changed the effective concentration at the surface of a paint film from 50-day lifespan in just permethrin and paint to being over 8 years, over 3,000 days, having an effective amount at 10 microns from the surface. So what is the nanomaterial that we actually chose? We decided to move forward with a carbon nanotube functionalized with polyethylene glycol. This is a high surface area material which allows us to load at to load our molecule onto it, or stick our molecule to it, at a much higher percentage than material that is not nano size. The material itself that we're loading onto it is the green molecule, and everything that's in gray is our loader, which is what we are trying to investigate. Scientifically, this has been proven to have an over 400 weight% loading with doxorubicin, which is an anti-cancer drug. And in this paper, they also demonstrated that the interaction of the molecule to the loading device was due to pi-pi stacking interactions. So this is the electron clouds around the CNTs. We're interacting with electron clouds in the aromatic groups of organic molecules, and that would create a non-covalent bond, which gives you that stickiness for your additive to adsorb and desorb from the molecule as it travels. So this adsorption and desorption and the fact that the CNT is PEG functionalized makes it completely miscible into aqueous solutions. The hydrophobic and pi interactions are also present in the solution. So what we would do is we'd pre-mix the CNT PEG with an additive, and then when it's properly mixed and loaded, we can put it directly into the paint, thus improving the release profile. So due to the fact that it's completely miscible in any latex-based paint, there's an entire market that is now available to us. Also, the PEG functionalized chains increase the size of the molecule to the point where they no longer interact with each other, so there's no aggregation, they're very well dispersed, and they're also large enough to be immobilized into the paint matrix so that the nanomaterial will never leak out or aerosolize. So in summary, our material is such that any organic species with a cyclic or aromatic ring on it should interact in a positive manner, and thus creating this diffusion coefficient that will allow us to desorb throughout a paint film at a much slower rate.
Our validation team had to prove two properties of MilleMisceo in order to prove that it actually worked. First, we had to be able to prove that additives were able to load onto the MilleMisceo. Secondly, we had to be able to prove that molecules could unload off of the MilleMisceo. For testing, we used a fluorescent dye named fluorescein, which is commonly used by industry. To demonstrate loading, we showed that fluorescein, when it comes in close contact to MilleMisceo, or to any carbon nanotube, short-range energy transfer will occur when you try to fluoresce the fluorescein. This causes the fluorescence to be quenched, or to die out. As you can see from this graph, compared to when fluorescein is free, the fluorescence of fluorescein is decreased by a large amount when it is in contact with MilleMisceo. This proves that our MilleMisceo was able to load molecules. Next, our validation team had to prove that molecules were able to release from MilleMisceo. To do this, we painted two surfaces. One had paint plus fluorescein. The other, paint, fluorescein, and MilleMisceo. After running water off of both of these surfaces, we then checked the fluorescence of the runoff water. And what we found is displayed in this chart. Without MilleMisceo, the amount of fluorescein concentration, the fluorescence, increased over time. We washed it at 1 hour, 2 hours, 4 hours, and 6 hours after drying. With MilleMisceo, that concentration profile is nice and horizontal. This proves that our molecule was able to release additives. Our next test was with phenethyl alcohol. Phenethyl alcohol, you might know as a sort of rose smell. It's a fragrance molecule, and we thought that this would be a good application. However, unlike fluorescein, phenethyl alcohol doesn't exactly fluoresce. So instead, what we did was we mixed phenethyl alcohol with MilleMisceo in water. We then centrifuged the solution, and ideally, the MilleMisceo and phenethyl alcohol should have been pulled down to the bottom of the tube. We would then take out the supernatant, that is the top portion, redisperse it in more water, and centrifuge it a second time. However, as you can see from this graph, after repeated washings, the amount of both MilleMisceo and phenethyl alcohol decreased, which unfortunately proves that we cannot use phenethyl alcohol to load onto MilleMisceo. Our next tests were with Permethrin. Now, Permethrin is an insecticide. It's extraordinarily toxic to both insects and fish, but not so harmful towards humans. In fact, it's completely safe for humans. We performed the same tests and found the exact opposite result. Instead of being too bound to water, it instead just crashed out of water immediately. We then tried to experiment with different solvent mixtures using varying levels of ethanol, and we were unable, the results proved inconclusive as we were unable to prove it either way.
So although Permethrin was unable to be conclusively proved to have loaded to the substance, to our loader, which is MilleMisceo, we still went forward with doing some insect testing because as a very hydrophobic molecule, we think Permethrin will natively also stick to MilleMisceo, besides the fact that it should also have favorable interactions with it. So we went into doing some insect testing. We talked to a professor who was doing fruit fly tests, and we also checked on CCAC to make sure that we were cleared the ethics board. And there's no indication that insect testing is on the same scale as animal testing. So we went forward with mortality studies, and after exposure to a painted surface that included Permethrin, the insecticide, which is a neurotoxin, so it takes a long time to take effect and overwhelm the neural firing of an insect, as well as MilleMisceo, and then we took Permethrin by itself with just paint. Both of those surfaces, when dried, had an effect. They were able to kill off the bugs within 24 hours, which would be part of our design goal, to remove any bugs from the surface. However, when we went into exposure and runoff tests, we would run water or soap water onto the paint films and look at how much is leaching out of that film. In the case where we have a commercial insecticide and a paint film, it was much more toxic to insects, killing them within less than a minute, compared to the exact same procedure being done with our MilleMisceo sample. It was still toxic, however, there was just much less toxicity present, and the bug died in about 10 times the amount of time. So this proves two important and key parameters. First, that our effectivity is still valid, and that when we are running off of the sample, we're losing less material. We're going to have if we put it into external applications, our surface will retain more effectivity over a longer time frame because it's losing less material. Secondly, what material does wash off is diluted. It's going to be less effective at causing environmental damage. So both of these are important results. Finally, we have to think about paint aesthetics. Because carbon nanotubes are a carbonaceous species, when you put them in solution, they turn to be very black. We were a bit skeptical at first because when you're adding black to a paint, you don't know what it's going to look like in the end. And that's kind of the key characteristic of a paint film, is the color. So this is actually a 3 times loading. So this is 3 times more carbon nanotubes that we'd included into this sample than we would normally. And the result is, even after this much being added, that you still maintain a white film, although the color seems to be very slightly changed. However, at our normal loading, and with different colors, we can find that there's almost an indiscernible change between samples that have MilleMisceo and samples that do not. In fact, you can go and check out our booth and feel these and touch and look at them yourself and try to figure out which one is which. So, as a type of conclusion, we were looking at 3 main product designs. First, we had to control the loading and the release profile to extend the lifespan so that our product would be effective. Secondly, we had to minimally affect the aesthetics such that our product isn't going to change the basic characteristic that people are originally buying paint for, and that's color and gloss. And thirdly, we had to make the solution somewhat comparable in cost. So we can state with certainty that we observed loading. We saw loading of fluorescence. We believe that loading of insecticide occurred, and we also feel that any aromatic species with enough aromatic groups should be able to interact favorably with our carbon nanotube and PEG functionalized loading system. Secondly, the aesthetics was not really changed. The paint films that we looked at and that we've been presenting, people have had a lot of trouble trying to determine which one was the one that has the additive included. Finally, making the solution comparable in cost. Because PEG functionalized CNTs are a relatively new concept on the market, they were first synthesized about 10 years ago, there have not been significant advances in how to scale up this process. We had to purchase ours from a company in California at a cost of about $1,100 per gram, which is much, much more expensive than you would have to pay for regular CNTs even. This cost should be decreased by magnitudes with the scale up in the production, as well as if there's enough demand for it. And we think that in the paint market, there's enough application worldwide that would drive this type of cost down. So, we've created a material that interfaces between the additive and between your paint to make it effective for a much, much longer period of time with a controlled rate. All that we need to do is choose the additive specifically that interacts with our molecule, and then we can put it into any paint surface. It's the key material in painting a ship's hull to make it so that barnacles no longer form. It's the key ingredient to allowing a surface that's treated with insecticide to be used on an outdoor external surface. It's the key ingredient that will make a fragrance stick around for more than 6 months. And so, as you walk through the next 10, 20 years of life, we hope that you'll stop and smell the scented walls on the way. Thank you.
Okay, questions? Very good promotion. So what is your product?
Sorry?
Product looks like powder, looks like a solution.
It would be in solution. So our product would be an aqueous solution because we don't trust it being a powder. So it would be an aqueous solution
What's the looks like? Is the color?
The color of the product
Black.
would be a black solution. If you saw in the one slide that was 3 times more concentrated, there was a pipette in there that included it was a black solution in there. It'd be slightly lighter colored than that, but still.
Then you will change my painting color. I don't like it.
We
can say is
tested.
that despite using a very black liquid, as soon as you incorporate it into the paint, because paints have binders, they have pigments, they're designed to essentially cover up whatever is behind them. And so these same pigments very conveniently will conceal our product within them.
So we just need to convince the consumer that when they're adding this black substance to their paint, it's not going to change the color by providing them with visible examples of that.
You can come by our booth, and we have samples available for you to look at.
So, so if the mechanism is correct, then why not use like multiple components? It would be cheaper, right? Only survey, right? Survey interact with your whatever.
Trade-off between single versus multi-wall.
Yeah, multiple will be much cheaper.
Multi-wall would be much cheaper, but the issue with single versus multi-wall is that with multi-wall carbon nanotubes, you're increasing the carbon content, which can more potentially increase or
The
change
color.
the color. So, and without changing the surface area available to you. So single wall carbon nanotubes are ideal for performance, but there is of course a trade-off between performance and cost ultimately.
Oh, okay, good consideration. So any other questions? Okay, no more, let's move on. Thank you very much.
Thank you.
Thank you all.